And then let's open up the first packet and obviously share that. All right, so as I said, we just took our second test. So we just got done doing all of the integration methods, and that's a very important part of Calc 2. But after that really intensive calculation portion of the course, we kind of get to slow things down and look at sequences and series. So first off, what is a sequence? Well, a sequence is just a list of numbers that follows some pattern. So for instance, 1, 2, 3, 4, 5, right? That's a list of numbers that are all increased by 1 from the one previous, right? So they're following a pattern. But they don't always have to be based on the number prior. So for instance, it could be, the sequence could be 2n. It could be 2 times the number. So 2 times 1, 2 times 2, 2 times 3. Right? That's not necessarily based on the previous value. And the thing that we're going to do the most in this section is prove whether things converge or diverge. And so you're probably saying, okay, that's great. What does that mean? Well, the basis for it is that if something converges, then it's useful. And if it diverges, it is not useful. And what it means to converge for a sequence is that the sequence approaches some value. So I don't care how many numbers I plug in, but as I plug in larger and larger values, I should be approaching some number. So the idea is when n approaches infinity, what value does the sequence approach? And for it to diverge, well, that just means basically that it's not approaching a particular value. So these first two problems here ask us to plot the first 10 corresponding values. So I'm going to go ahead and do that in Mathematica. Okay. So my sequence was -1 to the n times 2 to the n divided by n factorial. Now, before I do this, let me ask you this question, and I would like you to give me some response if you can. How many of you are familiar with factorials?
I am.
Okay.
I am.
I am.
So already it seems like more of you than normal are familiar with them, but let me just quickly give you a review on factorials. Just to be safe. So I'm going to pull up the whiteboard here. You guys can see that now? The whiteboard?
Yes.
Yeah.
All right, so factorial. If I had, say, 3 factorial, well, that just means 3 times 2 times 1. So it just means the number multiplied by every subsequent value down to 1. So if I had 5 factorial, That would be 5 times 4 times 3 times 2 times 1. Okay. And the neat trick here is that I can stop at any point. So for instance, 5 factorial I could write as 5 times 4 times 3 factorial. And this will come in handy later today. So if you notice, the next number in the factorial is the original number minus 1, right? And then this number is the original number minus 2. So if I replace the original number by, say, some n, then I could do n factorial, and I could write that out. So that's going to be n times n minus 1 times n minus 2, and I can do this all day long. So I'll just stop there and say n minus 3 factorial. And if I had n plus 1 factorial, for instance, that's n plus 1 times n factorial. Or I could break it down even further. And stop here, for instance. Okay, so it's always subtract 1 from whatever the value is that you start with and multiply it as you go down. So any questions about what a factorial means before I continue? All right, so I want to go back to Mathematica then, because I want to plot this sequence. And I believe I want the command discrete plot. The reason for that is because a sequence is a set of values, right? It's not a line or a parabola or whatever kind of curve it would, create. So then the points are not connected. So -1 to the n, 2 to the n over n factorial. And let's see, I think I need to tell it n, start at 0, and go to 10. Okay. Actually, I don't think we typically want to start at 0. Let's go 1 to 10. All right. So you see the values there. I don't like the line. I think that's filling. There we go. All right, so now we have a bunch of discrete plotted points, right? So if I asked you, what value does this sequence seem to be approaching? Could you tell me?
Yes.
All right, what does it seem to be approaching?
0.
So it looks like it's heading towards 0, right? And that doesn't matter if I have 10 points or if I have 1,000 points, right? Which is kind of hard to make out. Let's try maybe 100. Even then, right, we can still see all these little dots here, pretty much on the axis. So it only asks us to do the first 10. And even then, we can see that this thing is approaching 0. So we would say, let me jump back here. We would say that this is a convergent sequence, and it converges to 0. Now, obviously, you're not going to have this computer program in your hand when you go to take the test. So if you have your calculator with you, I'd like you to try this for part B. So when you all have your calculator, let me know.
I'm ready.
Change the mode. Let me get a little more light here so I can show you what I'm doing. All right, so if you go to, let's see if I can get this on here, mode, notice the 4th line down. It says func for function. And then the next one says, I think is PAR. The next is POL. And the last is SEQ. That SEQ stands for sequence. So scroll all the way over to it and hit enter. So now when you look, it should be highlighted. And now when you go to y equals, you should see this screen instead. Okay. So for u of n, that's what we're going to plug in our sequence. So for this problem, our sequence was -1 to the n. And then we need times, I'm going to put in parentheses. And the way to get n, by the way, is to just use the variable key that you normally would use. So the variable key that's x, t, theta, and n, use that guy. Now we need a factorial. So you're going to go to the math key. Okay. Then you're going to scroll over all the way to the right where you see PRB, that's probability. And you're going to choose option 4. So you see the little exclamation point there. So choose option 4 and notice that put the little factorial in there for me. So I'm going to close that up. And then it was divided by 2 to the power n.
Power n was on top. Oh wait, we're doing the second one. Never mind.
Yeah, we're doing. So I hit graph, and it's kind of hard to see because they are little dots, but those are the few that I got plotted. Can you see those? The reasons the others aren't on the screen is because they're just bigger than my scale. So while you guys are trying that real quick, I'm going to go ahead and plot that on Mathematica as well.
Now, where did you say? I couldn't find. Is the N in? What do you mean the fars button? Like my hit fars the Well, I see Y fars, but I don't see anything for N.
Can you? I'm not sure what you're asking me, Dan.
I'm sorry. Can you just go over how you found N again?
Oh, do you mean the variable n?
Yes.
It's just the x key. The key that you.
Oh, okay. I see it. Oh, okay.
It's x, t, theta, and n.
Mm-hmm.
So if you're in the normal mode that we use, this variable key is x.
Okay, I got you.
Mode it uses n, and so on.
All right, thank you.
Mm-hmm. And were you able to find the factorial okay?
Yes.
Okay. All right, so hopefully you guys can see my Mathematica page now. So I went ahead and plotted this in here as well, because it automatically does the scale for me. So now you can see that these, the first, say, 6 points are okay. By the time you get to 7, looks like you're already at, let's see, -50. And then the 8th point is at 200. And then the 9 and 10th point are off my scale already. Let's see if I go to maybe 15. It does. So now it gives me my 10th and 11th point. Regardless, you should be able to tell that these points are not closing in as we read from left to right. They're spreading apart. So that tells us that instead that this is divergent. So does that make sense to everybody? So Hannah, I saw you asked a question about what the input looks like. So it should be u to the n is -1 to the n in parentheses. And then another set of parentheses, I put n factorial inside there. And then divide by 2 to the power n.
Thank you, I got it.
You're welcome. All right. So that is the basis for the graphical representation of a sequence. So this one diverges. So basically, again, if the points come together and look like they're heading towards a single value, it converges. If they're spreading apart, it diverges. So as I said, that's the way to graphically do it. We can also do this using our analytic methods that we've learned in the past for limits. So it says here the limit of a sequence, where the sequence is some a sub n, can be written as the limit as n approaches infinity of that sequence a sub n equals some value L. And it says here in these two little points, if L exists, meaning it is some value like 5 or -1 million, then the sequence is said to be convergent. If L does not exist, meaning infinity or -infinity, or just flat out does not exist, then the sequence is divergent. So let's try a few of these. So it says determine if the sequence is convergent or divergent, and if it's convergent, give the value it converges to. All right, so we need to take the limit as n approaches infinity of a sub n. And I always forget to change this darn thing. Make this 7n. Otherwise, it doesn't make much sense the way it's written. So the way that we should have learned to solve infinite limits is to compare the order of the numerator and denominator, which you might recall doing. It is kind of a way to look at asymptotes. And so what I'm going to do is take the highest power of n from the denominator and divide everything by that. So in this case, it is n squared. So I'm going to divide every single term by n squared. And I'm sure some of you are going, well, that's great, but why are you doing that? So I will show you in just a second. So I divide everything by n squared. And if I now simplify, what does this look like? Well, I have 3 on top. This is still 1 over n squared. This is minus 5. And this is plus 7 over n. Okay. Well, now we have to remember some rules of limits. The first one being that if I have the limit of a bunch of things multiplied or divided, I can take the limit of each piece separately. And that also works for addition and subtraction. So I can basically take the limit of each term. So limit of 3, limit of 1 over n squared, limit of -5, and so on. The other rule that I have to recall is specifically for infinite limits. It says that if, I'm trying to remember what variable I want here. Yeah, it's x, that's fine. Okay. So if I have something that's 1 over x to a power, and said power is positive, then if x is getting really big, so is x to that power, and therefore 1 over really big numbers tends towards 0. Is that ringing a bell or make sense to everybody?
Yes, it does make sense.
Okay. So I'm using that fact and I'm taking the limit here. So limit of the top, well, that's just going to be 3. And on the bottom, this is going to head towards 0 because it's n to a power. So is this. So I got a number out of the limit. That means that I am convergent, or this converges. And it says if convergent, give the value. Well, that's our value that it would converge to. I think I'm going to leave this one for you guys to do. And I'm going to go ahead and do C. So again, I want to know, does this thing converge or diverge? So I'm going to take the limit as n approaches infinity of the C sub n term. So we can kind of deduce what's going to happen here, but it would be better. Let's go ahead and plug in approximately infinity, right? So what happens on the bottom? So if n's heading towards infinity and I plug it in, the bottom is approximately infinity, right? What about the numerator? What can you tell me about that one?
Wouldn't that also be going to infinity?
So it'll approximately be going to infinity as well, right? Do you recall anything about when you get infinity over infinity out of a limit? What that tells you to do?
It tells you it's in an indeterminate form,
Right?
and so you can use L'Hopital's rule.
Correct. So you can use L'Hopital's rule, which says I can go ahead and differentiate both the top and the bottom of this sequence and reevaluate the limit. So derivative of n with respect to n is going to be 1. Derivative of natural log of n squared is going to be 1 over the inside times the derivative of the inside. So that's going to be 2 over n when it simplifies, because one of these would cancel. So what's the limit as n approaches infinity of 2 over n?
Zero.
Right, I'm dividing 2 by really, really big numbers, which is going to become really, really small numbers or head towards 0. Okay, so I took the limit, I got 0. Does that mean I converge or diverge?
Converge.
So even though it's 0, I still converge, right? It is some number. I always like to say if you get something tangible, meaning something that you know how to work with, or that you can work with, then it converges. And the value that it converges to is 0. So I'm going to leave D for you guys to do as well. I think I'm going to go ahead and continue at least the first part of infinite series before I break you up and let you try some. So that was sequences. We would like to graduate to series now. And series is taking a sequence one step further because it is in fact just a sum of the terms in a sequence. So for instance, this first bullet here says the sum from 1 to 3 of I squared. So the sequence is I squared. Right, so you might write something like a sub I equals I squared. Which means any term here is just the number that you plug in for I squared. Well, the series is a sum of those terms. So we have 1 squared plus 2 squared plus 3 squared. And that's because our sum ran from 1 to 3. The next one down here runs from 5 to 9. So 5, 6, 7, 8, and 9. So notice we have 1, 2, 3, 4, 5 terms. Notice they have something that we're going to later refer to as an alternating term, because they go from negative, positive, negative, positive, right? They alternate sign. That's where that -1 to the k comes in. And then you just plug in 5 for the first one. So -1, this would be -1 to the 5th. And then 2 times 5, right? That's what we got out of that one. And then the next term would be -1 to the 6th, and 2 times 6, and so on. And then you just add all those up. So not much of a mystery there, right? It's just adding the terms that you would get from a sequence. But again, we want to ask ourselves the question, is this thing useful somewhere? And if it's to be useful, then it has to converge. So then the question is, well, how does it converge? So notice here on this bullet point, a series is said to be convergent if the sum equals L and that L is a real number. So basically the same idea as above, right? For the sequence to be convergent, we had to take the limit, and the limit had to give us some tangible real value that we could work with. And here, the sum just has to equal some real number. And for it to be divergent, just like the sequence, the sum has to equal some positive or negative infinity. So really big numbers or really small numbers. Or really big negative numbers is what I should say. Also note that this is for infinite series, which means we're running from some index n equal 1 or n equals, it could be anything, it could be 0, 2, 7, whatever. But the other bound has to be infinity. And sometimes that'll be written as just the summation symbol. So all that being said, actually, let me just give you this last little tidbit here, and then we'll go ahead and work some of these. So this line here is kind of important, and I'd like you to try to remember it. It says there's many series that are convergent, but the value L to which it converges either cannot be found or is not important. Now, why am I saying that? Well, the next two series that we learn, or our first two, we can in fact find their sums. Beyond that, we either can't find the sum or aren't really interested in what that value is. So at some point, I'm going to ask you, prove whether a series converges or diverges, and if so, find its sum. So if I tell you find the sum, it clearly has to be one of these two series. Okay. So I just want you to keep that in mind. All right, so the first one we learned is geometric series. And the geometric series has to be in this form. So notice when you write out the terms, every term has a in it. So realistically, you could write the summation as a times the sum n equals 0 to infinity of r to the n. But typically we leave the a inside. And it's just r to the first, and then r to the 0, r to the 1, r squared, r cubed, and so on. Another thing I want to note is, notice this one starts at 0, but I believe currently all of the problems here start at 1. So we could also start at 1. You could really start at any value, but we're going to just focus on 0 and 1. And the reason I bring that up is this next bullet point. It says the series starting at 0 is convergent if absolute value of r is less than 1, and the sum of the series then is equal to this guy. Now, it's still true that r has to be, or the absolute value of r has to be less than 1 if we start the summation at 1. But if we start at 1, so maybe I'll say s sub 0 and s sub 1, then the sum is now ar over 1 minus r. I know I'm throwing a lot of stuff at you, but we'll do some problems and hopefully it'll kick in. So the important thing right now is, how do I make a geometric series, or how do I make a series look like a geometric series? And it converges if absolute value of r is less than 1. Otherwise, diverges. So let's try a few of them to see if this starts to make some sense. So we're asked to determine if the series converges or diverges. If it converges, find its sum. So I'm starting here at A. Now this looks close to the form, but notice this R, which is conveniently named R because it is often a ratio, needs to be to just the power n. Well, I have a ratio here, but it's to the power n minus 1. So I need to do a little bit of algebra. I'm going to rewrite this as 3/5 to the n times 3/5 to the negative 1. So that's a property of the power there. Right, I have same base. So if multiplied, I would add the exponents, which is the same thing as what I did here, but in reverse. 3/5 to the negative 1 means basically just flip that fraction over. So I did that and multiply it by 2. So now I have sum from n equal 1 to infinity, 10/3 times 3/5 to the n power. This is now in the correct form. There is a number out in front that I can call A, and there is a ratio to the power n that I can call R. For convergence, I need to prove that the absolute value of R, which in this case is absolute value of 3/5, is less than 1. Obviously, that is the case, right? 3/5 is smaller than 1. So this converges. And we'll say by geoseries. So we've proven that it converges. We're then asked to find the sum. So the sum is something you have to pay attention to your index for. So this starts at 1, which means I need to use the sum for starting at 1, or the thing I called S1. So S1 is A, which is 10/3, times R, which is 3/5, all over 1 minus 3/5. So it looks like the sum comes out as 5 for that one. So converges, and the sum is 5. I think let me do maybe 2 or maybe 3 more of these, and I'll let you guys try the rest of them. let me go ahead and do. I'll do this one. And I think maybe this one for you guys. And I'm also going to change this to start at 0. All right. So first I got to try to get this in the correct form. So I'm going to start breaking this up. This is e to the n times e to the first. And on the bottom, I've got pi to the n times pi to the -1. So I'm going to put the e over pi together because they're both to the power n. And then I have e to the first and pi to the -1. Pi to the -1 means take it up to the numerator and make it positive. So there's a pi times e out in front here. That now is in the correct form, where this is a, that is r. So my question is the absolute value of r less than 1?
No.
Are you sure? All right, e is something like 2.7 and pi is 3.14. So it is slightly smaller than 1. Right, because that's true and that converges. And if we want the sum, our sum here, our series or our summation starts at 0. And so looking back up here, notice if we start at 0, then we need a over 1 minus r. So a was pi e. This is 1 minus e over pi. And I think the only thing I did for this one to clean it up was just multiply through by pi on top and bottom. Just left it like that. Of course, you can get a decimal for that, but exact answers are always better. Any questions about that guy? So this stuff is certainly not calculus intensive, at least not at the moment. Does require a lot of algebra, but other than that, it's not bad, and other than having to recall all of the rules. All right, so let me do E for you, and like I said, I'll let you guys break up and try some. So again, I need to try to get something to the power n. So I need to start breaking this thing up until I can get that. So the first thing I notice is I can make this 2 squared times 2 to the -n. So maybe I could write that like this. Right, 2 to the negative n means put it in the denominator, make the power positive, and 2 squared is just 4. But I still don't have this to just the power n. Any suggestions on how to do that?
Could you make it 3 squared over 2 to the power of n?
So what am I doing with this n is the question then. Did you mean this?
Yeah.
That's okay. That's good. So this guy here, right, is really 3 squared all to the n, which means I can then write it this way. Right, and 3 squared is just 9. So I have 9 halves to the n times 4. Or if you really want, you could put the 4 in front. So that it's a times r to the n. So a equals 4. R is 9 halves. We need the absolute value of 9 halves to be less than 1. Is that true?
No.
Right, that's not true. Therefore, this diverges. Now, here's the biggest thing I always see people try to do now is to go, okay, let me find the sum. It says if it converges, then you can find the sum. If it diverges, that means that there is no, or the numbers aren't getting closer and closer together. They're spreading apart, and therefore you could add them all day long and never get to a value. So there's no point in trying to find the sum if it diverges. So I would like you guys to take a minute or a couple. See if I can-
I just had a quick question. So before we were doing this series, we were using the limit to calculate like when or where a series converges at. Is there a relationship between the sum and where a series would converge?
So for a series, the sum is the value to which it converges, yes.
Okay, that makes sense. Thank you.
But remember, that's not the same thing as with a sequence. When you ask, does it converge or diverge, you're asking the question, do the points approach a single value over time?
Right.
For a series, you're asking, if I keep adding all these numbers together, do I get down to a value? And then, I might add on a couple more numbers, but they're so small that they don't do anything to my total.
Okay, that makes sense.
All right, so it looks like I left B, C, and F here under the series section. And under the sequences, I left you D and B. Do you guys have access to these? I gave you the notes already, so you should be able to pull them up or have them written down already. Do you need me to try to put them all on one page for you?
No.
So you could just make it 1 over the square root of 2, all to the n power for that one.
Okay, thank you.
And then another one I just wanted to point out in case anybody didn't get to it. I know I talked to a few groups about it. Go ahead and share it. Was this guy F? Wanted just to make sure that you knew that you could break this into 2 sums. And then you just treat both of them. So these both converge. And the thing I wanted to point out was if one of them didn't converge, if one was divergent, then the original series also would diverge. So say instead I gave you this one to start. And you broke it up into 2 parts. This one would diverge. And therefore, I don't care what this one does at that point. This also would diverge. Handwriting's terrible. Come on, erase. So I just wanted to point that out before I continued, in case you didn't get a chance to do that one. So the last part of this packet is telescoping and collapsing series. And these are kind of interesting because as you see here, it says almost all of the inner terms are opposites and therefore cancel. So if you see one of these terms, and a good way to identify them is a factored or factorable denominator. All right, so notice n times n minus 1. Down here we got n squared minus 7n plus 12. So if it's something that looks like it can be factored or is already factored, then you could look to see if it might be a telescoping series. So it says write out several of the terms of the series, then evaluate the limit of that sequence. Well, we can go ahead and evaluate the limit at the beginning, right? We should know enough about limits now. So n goes to infinity. 1 over n times n minus 1. So yeah, it looks like we're going to get infinity times infinity on the bottom. Or if we really wanted, we could multiply this in. It'd be n squared minus n. We'd have some kind of weird infinity minus infinity thing going on. Regardless, we know that the bottom is continuing to grow. and it's infinite. So this is approximately 1 over infinity, which we should know heads to 0. And it says here, the limit should go to 0. If not, it is divergent. So this tells us that it converges. If it converges, well, then we can continue. If it doesn't converge, there's no point in trying to prove that it's telescoping and therefore find its sum. So notice it says a partial fraction decomposition may be necessary. So that's why I said if it's something that's factorable, well, then it would lend itself to partial fractions. So let's do the decomposition. I would need a over n plus some b over n minus 1. These are both linear distinct factors. And this has to equal 1 over n times n minus 1. So I would multiply a by n minus 1, and I would multiply b by n, and this would all have to equal 1, right, the numerator. So I get a plus b times n minus a must be 1. There are no n terms on the right, so a plus b must be 0. And negative a is a constant, so it must equal 1. That very clearly tells us a is 1. Sorry, negative 1. And if that's the case, well, then that quickly tells us that b has to be positive 1. So our sum, which before was 1 over n times n minus 1, can now be replaced by these two terms. So we'd have negative 1 over n plus 1 over n minus 1. And the sum runs from n equals 2 to infinity. So you got to be careful and pay attention to that. So I know I did that decomposition quickly, but it is by no means a difficult one. Is everybody with me?
Yes, I'm with you.
Anybody else want to give me some reassurance?
Yeah, I'm good.
All right. So we've proven that it converged. We now have the decomposition of the telescoping series. So all we need to do now is start plugging in numbers and see what happens. So I'm going to let n equal 2. It's going to be negative 1 over 2 plus 1 over 2 minus 1. Then I let n equal 3. So plug in 3 for n everywhere. Then I let n equal 4. And 5, and so on. So then simplify that. So I have minus 1/2 plus 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1/4, and so on. So what cancels? Well, I've got minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4 plus 1/4. You should be able to deduce that the next term is going to have a 1/5 in there. So that minus 1/5 would cancel with the next term. The only thing that remains is 1. So this converges, which we proved from the limit, and the sum is 1. So one of the questions you might have is, well, what happens to all these terms as you get out further? Well, notice the denominator is increasing, right? And I have infinite amount of terms. We've already discussed many times today that 1 over really big numbers heads towards 0. So even if you're not sure if those fractions would cancel with the next term, each fraction starts to get smaller and smaller until they're basically 0 anyway. So just to recap telescoping, if you see something that looks like partial fractions is a good idea, right? Because it is something that's factored or can be factored. Then you should test it by taking the limit as n approaches infinity. If it returns 0, then that series, if it is telescoping, converges. And to find the sum, you need to do the partial fraction decomposition, write out the first couple terms, and determine what's left over after those terms cancel. So I'm going to leave this one for you guys to do, but I want to go ahead and start 1 to 2 more topics before I let you guys work some more problems. So is there any questions about this particular problem?
So I'm still a little confused as to how do you like identify to know to use the telescoping, or how you know that it's the telescoping series.
So in order to identify if it's telescoping, you'll see something that's already got some factors in the denominator, or that might be factorable.
Okay.
So some kind of polynomial. If you see that, then you can, obviously, the idea here is that through time, we're going to learn, 10 different ways to test a series and probably 12 different types of series. So when you see something, the idea is, okay, what tests do I use? And so you want to start identifying forms and which is the best test to use. And so the best I can say for right now is if you see something that's got a polynomial of some kind in the denominator, one of your thoughts should be, is this a telescoping series?
That makes sense. Thank you.
Another one, right, for the geometric, if you see a bunch of stuff to the power n, your brain should be thinking, okay, can I get this down to some number times another quantity all to the power n. All right, so I'm going to stop sharing that guy. And I will open up the other packet. So we learned so far geometric and telescoping series. And as I said, we're going to learn a ton more. The first one, well, this is actually just a test, and it's called the test for divergence. So this is a powerful tool, but it's also fairly limited. And I say that because if you show that the series diverges, you're done. But if it doesn't diverge, you cannot jump to the conclusion that, oh, it must converge, right? So notice here in the bold, it says, if the limit as n approaches infinity of a sub n equals 0, this does not mean that the sum converges. So test for divergence is only good to show us if something diverges. And how does it do that? Well, again, you take the limit of the sequence, right, the a sub n term out of the sum. And if it returns does not exist or any number other than 0, it diverges. So if we get 5 or if we get infinity, right, that tells us that thing diverges. If we get 0, we have to say inconclusive. And all that means is you better use another test. So let's take a look at one of these guys. So it says use the test for divergence to determine if the following sequences diverge or converge. Sorry, if the sequence diverges or it cannot be determined. So again, this one here, it's got a nice polynomial on the bottom. So your instinct might be originally to try telescoping. But let's see what happens if we use the test for divergence. So I want to take the limit as n approaches infinity of the sequence. And you could do this a couple different ways. If you really want, you could divide through by n squared if you don't like the way that it looks right now. So when I do that, what happens? Looks like these are going to go to 0 because they're divide by infinity, right? Divide by big numbers goes to 0. This one here also goes to 0. So I end up with 0/1 or 0. Well, if I go back up and look at the bold up here, it says if the limit gives me 0, then that does not mean it converges. Rather, it means inconclusive. So guess what? It probably would have been best to treat this as a telescoping and try that. So if you have time today, you can try that and see what happens. think I'll leave this one again for you. Let's look at C. Again, because it's test for divergence, I just want to take the limit as n approaches infinity of a sub n, which is arctan of n. Now, it's perfectly okay that you have no idea what this function does out at infinity, at least analytically. This one's actually better if you graph it. So you might recall arctan looks something like this. And it has this asymptotic behavior. Do you know what these two lines are?
Is it pi over 2 and negative pi over 2?
Yes, sir. So now if I asked you what's the limit as n approaches infinity of arctan of n, what would you tell me?
Pi over 2.
So yeah, as n gets big, right, we would approach this line pi over 2. So if the limit does not exist or gives back some number that is non-zero, the series diverges. All right, let's go ahead and try this last one here. So again, I need the limit as n approaches infinity. I'm going to rewrite 3, or the nth root of 3 as 3 to the 1 over n power. So this is approximately 3 to the 1 over infinity. 1 over infinity is approximately 0, and 3 to the 0 is 1. This is a non-zero number, which means diverges. So I'm sure already you're probably getting a little overwhelmed with all of the rules. So may I suggest start making a note card with each type of test and its rules. Because there's going to be a ton of them and it's going to be hard to keep them all straight. So any questions about test for divergence? Right, it basically says take the limit as n approaches infinity. If you get 0, it tells you nothing. If you get anything else, it diverges. All right, I'm going to leave that last one for you. I think I'm going to go ahead and look at P series. And we'll see if we get through integral test. So I want to give you guys some time to try some problems. So P series, let's see, I will do this one. And I guess maybe this one. All right. So first off, what does it mean to be a p-series? Well, a p-series is of the form 1 over n to the power p. So p-series, p is the power. And p has to be some real number, obviously. If p is greater than 1, then the series converges. If it is less than or equal to 1, it diverges. And one of those is a very special case. And the teacher that I had when I had this course absolutely loved it. It's called the harmonic series. And it's the specific case when p equals 1, which falls into case 2 here. All right, so the sum, if p is 1 over n, which is referred to as the harmonic series, and it is divergent. So if I ever give you a problem and you see this, all you have to do is just say harmonic series, therefore divergent. So it's a really well-known series, and we know that it diverges. All right, so we're looking for, is p greater than 1? Then we converge. So let's find out. We've got to get it in the form 1 over n to a power. Okay, well, this first one here, I can just write as 5/4 times 1 over n to the 15th. And this 5/4, if I really wanted to, could get thrown out in front. Right, there is no n in it. Therefore, it can go in and out of the sum freely. So now this looks exactly like what I expect, 1 over n to a power. That power p in this case is 15, which is obviously greater than 1. Therefore, converges by p series. All right, well, that one's pretty basic. We found p. It was 15. It's greater than 1. How about d here? Well, this looks like one of those cases where I should split it up. So let's make it into 2 summations. First one being 2/4. And then we've got n cubed over n to the 2/7 plus another sum, which is 3/4 n squared over n to the 2/7. So the 2/4, that can come out as a half. N cubed over n to the 2/7. So I need to do 3 minus 2/7. So that's 19/7, right? Ooh. Then this one I can pull the 3/4 out. Then we have n squared over n to the 2/7. So that's n to the 2 minus 2/7, or (12/7), right? But these are in the numerator, and my p series is always 1 over n. So I need to come down here and rewrite these as 1 over. Computer's starting to act up. Okay. So I broke it into two sums. I simplified them the best I could and wrote them as 1 over n's. However, notice that for this first one, p equals negative 19/7. And I want that to be greater than 1 for convergence, but it's not. It's less than 1. So this diverges. And just like I told you guys earlier, if one piece of the original diverges, then I don't care what the other one does, which also in this case diverges. The original automatically diverges. So I left you B, C, and E for this one. I think I'll go ahead and break you guys up and let you try these problems. So you have the telescoping, you have this guy right here for test for divergence, and then you have these three for P series that I would like you guys to do. Guess we can probably get integral test in tomorrow. Just take a look at what we have scheduled for tomorrow. Comparison test, alternating series. If we need alternating, can get moved to go along with the ratio and root. We should be fine. So do you need me to go to any screens so you can write them down, or are we all good to go?
What were the two test for divergence problems you wanted us to do?
Test for divergence is just B,
Just B. Okay.
but then there's also the telescoping that I left from the last packet.
Okay.
Would you like me to pull that one up?
No, that was just B, right?
Yep. All right, so I'll go ahead and put you guys in your groups.